WOW signal. On August 15, 1977, the Ohio State University Radio Observatory's Big Ear Telescope detected a 72-second narrowband radio burst at 1420 MHz, the natural emission frequency of hydrogen. This frequency choice was significant because hydrogen is the most abundant element in the universe, making it a logical target for anyone deliberately sending interstellar signals. The burst originated from the direction of the Sagittarius constellation, a region rich in stars and gas clouds, but no definitive astronomical source has ever been identified. Jerry Amon, the astronomer analyzing the data, circled the anomalous spike on the computer printout and famously wrote "WOW" in the margin, cementing the event's name in scientific history. Despite decades of follow-up observations using Big Ear and later telescopes, no repeat signal of the WOW burst has ever been detected, fueling speculation about its origin. Explanations have ranged from natural astrophysical phenomena to passing comets to the possibility of extraterrestrial transmission, though none have been confirmed. The combination of its strength, narrowband nature, and precise hydrogen frequency continues to challenge conventional explanations. Because the event remains unresolved, the WOW signal stands as a starting point for the modern search for unexplained radio bursts, leading directly into the discovery of fast radio bursts decades later. Lorimer burst. In 2007, Duncan Lorimer and his student David Narkovich uncovered a peculiar 5-millisecond radio pulse buried in archival data from the Parkes Observatory in Australia, originally recorded in 2001. The event, later named the Lorimer burst, marked the first confirmed fast radio burst, a class of signals unlike anything seen before in astronomy. Its intensity was extraordinary, releasing an amount of energy equivalent to hundreds of millions of suns despite its fleeting duration. Because the signal showed signs of dispersion consistent with traveling through vast amounts of intergalactic plasma, astronomers concluded it must have originated billions of light years away. The discovery forced the scientific community to confront the existence of a powerful and previously unknown astrophysical process capable of producing such bursts. Since then, the Lorimer burst has sparked a global effort to track down similar events, with new observatories like CHIME and ASCAP now cataloging thousands of them. Repeating FRBs. The mystery deepened in 2012 when astronomers detected FRB 121102, the first fast radio burst ever observed to repeat, overturning the assumption that all such events were singular explosions. Located 3 billion light-years away in a faint dwarf galaxy, the signal stood out for its consistency, with bursts recorded in the same sky region across multiple years. In 2016, the Arecibo Observatory confirmed its repeating nature, eventually cataloging hundreds of pulses with varying intensities and intervals. Unlike the one-off Lorimer burst, this signal proved that some FRBs originate from persistent or recurring astrophysical engines rather than cataclysmic destruction. Studies later linked the source to a compact, highly magnetized environment, possibly near a young magnetar formed in a recent supernova. Observations by the Canadian Hydrogen Intensity Mapping Experiment, or CHIME, expanded the catalog of repeaters and revealed that these bursts often follow strange patterns, strengthening the case for magnetars as a primary source. The confirmation of repetition opened the door to tracking their physical origins more precisely. Perseus Cluster Whistle. In 2003, the Chandra X-ray Observatory detected unusual pressure ripples in the hot gas filling the Perseus Cluster, a massive structure located 240 million light-years from Earth. Analysis revealed that these waves were generated by the central supermassive black hole, which periodically injected energy into the cluster's atmosphere. The oscillations corresponded to a wavelength equal to 57 octaves below middle C, far beyond the range of human hearing and lower than any note ever produced on Earth. Effectively, this discovery marked the detection of the deepest sound known in the universe, though sound here refers to pressure waves propagating through hot plasma rather than air. To make the finding more relatable, NASA scientists sonified the data, converting the ultra-low frequency ripples into audible tones that captured the eerie resonance of a galaxy cluster. The Perseus cluster's whistle demonstrated that black holes not only consume matter, but also shape their cosmic environments through mechanical energy. This strange insight into astrophysical acoustics set the stage for another class of unexplained signals, the erratic radio transients near the Milky Way's center. Galactic Center Radio Transients. In 2002, astronomers using the Very Large Array in New Mexico detected a puzzling set of radio bursts emanating from the direction of the Milky Way's center. The object, later designated GCRTJ 174530009, emitted 10-minute-long bursts at regular hourly intervals, a pattern unlike anything seen from known pulsars or stellar flares. Its brightness varied dramatically between detections, and sometimes it disappeared completely, only to return months later in unexpected form. Because its behavior failed to match established astrophysical categories, scientists struggled to explain whether it was a new class of neutron star, a highly magnetized white dwarf, or something more exotic. 2 decades of observations have not produced a definitive answer, and the source remains unidentified, continuing to challenge standard models of compact stellar objects. KIC 8462852, Tabby Star. In 2015, data from NASA's Kepler Space Telescope flagged KIC 8462852, later dubbed Tabby Star, as one of the strangest stellar objects ever monitored. The star, located about 1,470 light-years away in the constellation Cygnus, showed irregular dimming events of up to 22%, lasting from several days to weeks at a time. Such deep and inconsistent light dips were far too large and chaotic to be explained by conventional planetary transits, which produce predictable and shallow brightness reductions. Astronomers propose theories ranging from clouds of dust and swarms of disintegrating comets to unusual stellar activity, yet no single model explained all of the observations. For a brief period, some researchers and media outlets even speculated about the possibility of an alien megastructure, a hypothetical Dyson sphere partially obstructing the star's light. While subsequent studies found that fine-grained dust is the most likely explanation, the irregular behavior of Tabby's star remains a reminder that our models of stellar dynamics are still incomplete. Blazars and gamma signals. Blazars, first catalogued in detail during the 1990s, are a subclass of active galactic nuclei powered by supermassive black holes that aim their relativistic jets directly toward Earth. These jets emit high-energy gamma rays that can outshine entire galaxies, often varying in brightness on timescales from hours to weeks. Since its 2008 launch, the Fermi Gamma Ray Space Telescope has continuously monitored these sources, building a vast catalog of their violent outbursts and spectral signatures. Because of their variability and intense emissions, blazars can sometimes mimic the appearance of repeating radio signals, leading to confusion in the search for fast radio bursts. In several cases, candidate FRBs were later traced to blazar activity rather than entirely new astrophysical objects, showing how overlapping phenomena complicate the interpretation of deep space signals. Perytons. During the early years of fast radio burst searches, astronomers at the Parkes Observatory in Australia detected a series of puzzling signals that bore all the hallmarks of deep space transients. These bursts, lasting only tens of milliseconds, appeared sporadically and seemed to share some of the same dispersion patterns that had defined the original Lorimer burst. In 2015, investigators finally traced the perytons to an unexpected culprit: microwave ovens on site, which produced the signals when doors were opened prematurely. What once seemed like possible alien transmissions or exotic cosmic events turned out to be nothing more than kitchen appliances contaminating radio surveys. Despite their mundane origin, the perytons served as a critical reminder that not all mysterious signals come from the stars, and careful scrutiny is required before declaring cosmic discovery. Cosmic Dawn Signal, EDGES. In 2018, astronomers operating the EDGES radio experiment in Western Australia reported a surprising absorption feature in the sky-averaged radio spectrum at 78 MHz. This dip indicated that the very first stars, forming about 180 million years after the Big Bang, emitted enough ultraviolet light to alter the hydrogen gas around them. The absorption was nearly twice as strong as theoretical models had predicted, suggesting that the early intergalactic medium was colder than expected at that epoch. Because conventional astrophysics could not fully explain the depth of the signal, some researchers proposed that dark matter might have interacted with hydrogen, cooling it more efficiently. The cosmic dawn detection remains controversial, as follow-up instruments have struggled to independently confirm the result, leaving open the possibility of experimental error or terrestrial interference. If you enjoyed this, I'm going to be posting a lot here. I would greatly appreciate it if you could subscribe. Thanks for watching.